So today we're going to talk about clustering and the k-means algorithm. So what exactly is clustering and why is it important? So let's start with why it's important, so you get an intuitive understanding of why we have methods like k-means and EM algorithms, like why are they important. So well, first off, it's really important because it's an unsupervised method of learning. So no one has to really sift through a lot of data and label all of them manually. So that's a big advantage for anything that's unsupervised learning. Um, and you can use this on really large scale, just raw data, and it can classify that data into different clusters, which can be very useful because that can give you a sense like of the structure of the underlying data, and then you can build different models for each cluster if their behavior is if the behavior is decently different. So one place where they use this is in the insurance industry to predict the chance of someone having a heart attack, and so they train. So with all the raw data that they get, they run something like k-means algorithm on it to divide the people into different segments. Some will be extremely healthy, some not so much, different behaviors, different habits, and then train a different model in each one to predict um, the likelihood of them getting a heart attack. And like having those different models generalizes and predicts those specific clusters way better than having one general model to predict everyone's. Okay, so let's come to the k-means algorithm. Now, the the objective of this algorithm is to take completely random data, like we have over here, and then classify that into different groups. So the first step to do something like this would be to decide how many different groups we want. So for this, that's a hyperparameter. So for now, let's just go with 4. I'll talk about how you decide how many of these groups you want towards the end. But for now, let's just go with an arbitrary number, which is 4. So the next thing we do is we initialize these centers completely randomly, like the centers of these groups. So let's say we have one here, one somewhere here, one somewhere here. Initialize completely randomly. Now what we essentially want to do is we want to classify each one of these data points as belonging to one of these centers. So for that, what we do is for each data point, so let's say this one, we will find the distance between that data point in each and every one of those centers, and the one that it has the minimum distance from, we will classify it as being part of that group, of that center. So this one, so in our case, this one at this point would be part of this center. Okay, so after we do that, we move the centers to the mean of their data. So this point, this point, this point, this point, they're all part of this center, this group. Similarly, these points are part of, say, this one. These points are part of this one, and these points here are part of this one. So now we take the average of all of those points and move our centers to that location. So we take the average of all of these points over here and move our center to the average of those points. And we repeat that step iteratively till um, till the total distance essentially converges. So you'll get a graph something like this for the number of iterations, and it's fairly obvious to tell when it converges. Um, so let's just see an animation of that because I feel like that'll make it a lot more clear. So over here, this is the exact same data set. Um, we the 4 green points are randomly selected, and the distance of each point is calculated, and then each one is set to a specific center. And then the points are moved to the average of those centers, and then you keep on doing this process. As you can see, after each iteration, it moves a little less. So yeah, that's essentially the EM algorithm. It's really simple. So it's basically like mathematically. So you go from n is equal to 1 to n. These are your n data points. Now for each data point, uh, you check its distance from each and every one of the centers. So let's say x is our um, data point. So there are n of them. So x to the n, n being the nth data point. um, and xk minus, let's say our center is defined by p, the kth center is defined by p subscript k, and we take the Euclidean distance between them. There are other measures that can be used, but Euclidean distance is fairly straightforward and widely used one. Um, so this is essentially what you're trying to minimize, where x sub I minus p sub j, where I is not equal to j is equal to 0. This essentially, what this just means is we're finding the distance from the center that this data point is part of, and not from all of the centers. We just find the distance from all of the centers to classify it to a specific point, but when we're minimizing the total distance, we only count the distance from the center that it is a part of. Okay, so let's now talk about how we can choose k. There are various methods like the elbow method, which I'll talk about here. So this one in particular is the elbow method. Then you have the silhouette method and the gap statistic. I won't go into detail about those. You can read up on them if you want. Let's just write those down here. So how do you spell silhouette? Silhouette, I think. So you have the silhouette method and the gap statistic. Okay, so let's talk about the elbow method. So what exactly is this? Now, over here, you plot a graph with your distances, all of your distances on one axis, and the values of k on the other. So that is just what we mathematically defined over here. Let's copy that, paste it here. Okay, so this is what goes on the y-axis, basically the distance of each data point from its respective center. And I see this should be capital N. Anyway, and then as we increase the value of k, as we increase the number of clusters, the total distance will go down. And when we have exactly n centers, it will, in theory, just go down to 0. Obviously, since it's initialized randomly, anything could happen. But in an ideal scenario, so to say, the centers would just be the points themselves. So that just overfits the data tremendously. So plotting a graph like this and seeing the point of inflection usually gives a good idea of how many clusters you should have. Yeah, let's move on to bad local minima. One problem that you can run into using k-means is bad local minima. So let's say we have a data set something like this. Now, when we initialize points randomly, there could be a scenario where the centers are initialized like this. In this case, with further iterations, it's not going to move, the centers aren't going to move much. It's stuck in this local minima, whereas we can see that this isn't, in fact, optimal. Visually, something like this would be a little more optimal. So when using k-means, you want to just run your algorithm a few times just to make sure that one of your iterations isn't just getting stuck in a bad minima, and then you average over all of those. Now, instead of having a very hard categorization that this point, so let's say the ones in green are centers initialized randomly, this data point belongs to this and only this point. Another thing we can do is we can say that this point belongs to this point with a weight of 0.7, to this point with a weight of 0.2, and to this center with a weight of 0.1. We always want to keep the sum of all the weights to go to 1. So to do this, essentially what this is soft k-means. Soft k-means because it gets its name from the softmax function, which we use to calculate these weights. So how exactly that works is we take the distance of this point from this center, then we take the distance from this center, then we take the distance from this center, and then we take the distance from this center. And to see the percentage weightage that we should give, it will be the percentage weightage that this point gets will be Very simply put, this isn't the softmax formula, but just an intuitive understanding of what's happening. It will be this distance, so the distance of that point. So let's call this point 1, 2, 3, 4. So it'll be the distance of the first point, of the first center from your first data point, divided by the sum of the distances of all other centers. Um, this is to make sure that that all of it adds up to 1. So we actually use the softmax function for this, to calculate the weights that we should use. So what that essentially is we do exactly that, but we take it e to the power of that. We take it as an exponent. So it is, how we classified it earlier. We used x n to the points. Anyway, so xn sub k minus p sub k whole square. So that's just the distance of um, the data point from its specific center, the center we are considering right now, divided by, um, we sum from I is equal to 1 all the way up to k. Now over here, notice that it's x sub I minus p sub I, because here we're looking at the distance of that point from each and every one of the other centers. So that's soft k-means, and when we move the centers, the green points to the mean of the data points, we use the weights while calculating those. Yeah, so that's soft k-means. Okay, so we can finish off by talking about the runtime complexity of the algorithm. So let's say we have n data points and we have k centers. Now we are calculating the distance of each data point from each center. So we're doing n multiplied by k operations for that. Now let's say our data points are in d dimensions. So each one is represented by a vector, say x1 all the way to xd. So our centers will be represented again in d dimensions. So let's say y1 all the way up to yd. And if we're using something like Euclidean distance, um, that will be a total of this plus x2 minus y2 whole square, etc. So that'll be another d operations, so to say. So your total runtime becomes the O of nkd. You can make this more efficient by using something like principal component analysis to reduce the dimensionality. So in effect, you're just reducing d, which will make this algorithm run faster. Yeah, so that's pretty much it. This is actually a really useful algorithm, not just when it comes to clustering, like the idea and the intuition behind the algorithm. So in one of my interviews, for a quant position, I got a question that you have a bunch of data points. So let me just draw a bunch of points. So you have a bunch of points, not data points, sorry. And you have to write an algorithm that chooses the minimum number of points that are required um, to make a boundary. Like you connect those points and it makes a boundary that encloses all the other points. So something like this would work, but essentially the minimum number that would be required. And so this isn't, well, k-means, so to say, but the idea of k-means can be used. So my proposed solution for this was choose any random points. So you could choose something like that, any 3 random points, and join them, because to form a closed figure you need at least 3 sides. And then iteratively like go to every other point that's there and see if it's enclosed inside it or not. So if this is in an xy plane, then you can use the equation of the line to see the equation of the 3 lines to see whether they are the remaining points are inside or not. I won't get into detail about that, but yeah. So you can see, is this line inside? No, it's not. So then you can take away the connections and now include that point in your boundary. Then you go to the next point. Let's say this one happens to be the next one. Yes. So now this becomes your new shape, etc. And you iteratively do that till you get the final answer. So the idea of k-means and the approach behind it can also be very useful in other things. Yeah, that's about it. Thank you. And if you have any questions, feel free to reach out.